Hey guys, welcome to Safi Mixed. In this video, I want to find the solution to Schrodinger wave equation for a step potential, and we'll discuss the related physical concepts of the problem, such as the role of uncertainty principle and describe in understanding the existence of particles in classically forbidden regions. The solution to of Schrodinger wave equation in the presence of step potential helps us to understand the concepts of reflection and transmission probabilities, amplitudes, and the related probabilities for finding the particle. That is, it helps us to understand the probability of reflected particles, the probability of transmitted particles, and also in terms of the probabilities of incident particle. Additionally, the step potential can be realized in several situations of critical importance. For example, the interface between a normal matter and superconductor can be modeled in the form of a step potential. Similarly, the scattering of quasi-particles from a pair potential can be modeled in a step-like potential. Therefore, understanding the mathematical machinery for the solution of Schrodinger wave equation in the presence of step potential is very useful for several practical problems in physics. With that said, I would like to write down the equation for defining step potential, and I would prefer to carry on all the solution in one dimension. So I would like to write the potential in the x direction. Therefore, the step potential for our case we will consider as a function of x, and we write this in the form of a conditional equation such that the step potential is 0 when x is greater or equal to 0, and it is a constant equal to v naught when x is lesser or equal to 0 and when x is greater than 0. So the potential is constant for values of x greater than 0, and it is 0 for x lesser or equal to 0. And if I want to represent this graphically, it would go like this. This is x-axis. The x is increasing to the left, and here is the origin. I represent this with x is equal to 0, and the value of the potential goes like this. So in this region, the potential is 0, and in this region, the potential is constant equal to V naught. So I can write this as V naught. That's the value, the height of the potential is V naught. So that means we split the whole space into different regions, one with constant potential and the other with zero potential. So I represent the left region with, I would call this region 1 and would call this region 2. Our particle would either be in region 1 or in region 2, or simultaneously, as a quantum mechanical concept, the wave be existing in the two regions. And with this graphical representation, now we have two different scenarios. If the incident particle has energy number 1, E, the total energy of the particle is lesser than V naught, that is one instant, and the other, the total energy of the incident particle is greater than V naught. These two conditions, or the solution of Schrodinger wave equation under these two conditions, give rise to physically different results, to physically different scenario. And each condition has the right to be discussed separately. For that in mind, I would like to first consider case 1. That is, we will consider a particle with energy E lesser than V naught. And when that's the case, In region 1, the particle would behave as a free particle because the potential is 0. And region 2, the particle would behave as a bound particle. So we have a combination of free and bound particles of solutions for the Schrodinger wave equation. And I would do that separately for region 1 and region 2, and would then try to find the physical results jointly. So first I want to write this one-dimensional Schrodinger wave equation, and remember the potential is only position dependent, and then it is constant in one region and in another region, means the potential is totally independent of time. And when that's the case, we only solve the Schrodinger wave equation for position dependency and ignore, we don't spend time on the time dependency, because in such cases, as we have already learned, that the time dependent part behaves as a phase. So I would prefer to solve the Schrodinger wave equation for position. And with that in mind, I can write the Schrodinger wave equation as minus h bar squared divided by 2m derivative of the wave function, position dependent wave function with dx squared plus the position dependent potential and multiplied with the wave function psi equals e of psi x. Okay, that's the Schrodinger wave equation, and I want to solve this Schrodinger wave equation for each value of potential, that is for potential when this is 0 and for potential when it is constant. In other words, I want to solve this wave function for region 1 and region 2. And in region 1, I'll represent the wave function with subscript 1. In region 2, I would represent the wave function with subscript 2. So first I want to solve the Schrodinger wave equation in region 1, and for region 1 Vx is 0, therefore this equation straight away reduces to this simple form, minus h bar squared divided by 2m d squared psi 1. Since I'm solving this for this region, therefore I keep the subscript along, and then dx squared plus this term is 0, so I'm not writing that because Vx is 0 in this region, and I'm taking this term to this side of the equation. That would make minus e psi x, and the whole equals 0. I can remove the negative sign by multiplying the whole equation with minus, and want to put this term with this, and want to combine this term with the energy. Therefore, I put the equation into this form, psi ix divided by dx squared plus, because I'm multiplying with minus, so both terms would become plus, and then I can write 2m e divided by h bar squared psi of x equals 0. Now I want to, since this term e for a particle, for a given particle is constant, m is constant, everything in this factor is constant, therefore I redefine this as a constant factor, and traditionally we call this k or k1. Therefore I can put the equation once more in the form psi of x divided by dx squared plus k1 squared into psi of x equals 0. Obviously k1 squared equals 2me divided by h bar squared, and this is a constant, and remember this is a positive constant because nothing in this vector is negative, everything is positive, so k1 is a positive constant. And this is now a very familiar equation. We have seen this for the solution of simple harmonic oscillator, even in the classical case. So I want to find the roots of this equation first, and I do that by writing this over here in this region. So I can write this equation or factorize this equation by calling d squared over d squared is d squared plus k1 squared into psi of x equals 0. That is, I'm taking psi, this is psi 1 of x. Psi 1 common from both these terms, so I should put a 1 with this one. I missed that, so this is 1, this is 1. And now obviously the psi 1x can never be 0. The wave function cannot go to 0, and the product of these two terms is 0. That means the term inside this brackets goes to 0. So I write this as d squared plus k1 squared equals 0. And from this I can find the roots of the equation that d squared equals minus k1 squared, or d equals plus minus iota k1. So we have two complex roots, one positive and one negative. And we know from the from our calculus, from the solutions of second order differential equation, that each root corresponds to a solution, a separate solution. And the solutions for second order differential equation is either exponential or sinusoidal, and I would prefer to solve the problem in exponential form. So every complex root in this equation corresponds to a separate solution, and then the generalized solution, the superposition of the two solution, or linear superposition of the two solutions. Therefore I can write a solution to this one equation in the form psi 1 of x equals a times exponent the plus root iota k1x, and then plus b times exponent minus iota k1x. I call this an equation, let me call this equation 1. Now we have two terms in the solution. This one with the positive value is in fact representing the flux of incident particles, or the wave of incident particle, and this one represents the wave of reflected particle. That is, if I represent them, this term is a exponent iota kx, and then I have this term b exponent minus iota kx. That is, this term represents the incident wave, and this term represents the reflected wave. So here a and b are the probability amplitudes for the incident wave and for the reflected wave. And these are written arbitrary, but we can define their values from boundary conditions of the problem. And I will come to that after I find the solution in the second region. Now, if I write Schrodinger wave equation for the second region, for this region, I can put this into the form by writing this as psi 2, and combining this term with this, I can write this as minus h bar squared divided by 2m d squared psi of x in region 2 divided by dx squared plus v of x minus e and psi of x in region 2 equals 0. And I again combine this term with this term, and writing the equation in the form d squared psi 2 x divided by dx squared, and this would become minus 2m divided by h bar squared into v of x minus e into psi 2 of x equals 0. Okay, again, the term inside the bracket is a positive number because Vx is greater than E. So we are taking this case E is less than V naught, so V is greater than E. And I can even, instead of writing this in terms of Vx, if I'm writing this for the second region, then I shouldn't have this as Vx, rather I would write it as V naught. And so I put this as V naught because we know that in the second region the value is V naught. So I write it in this form. Now V naught is greater than E, therefore this is a positive term. Multiplying them with these positive factors leave this a positive number, and I redefine that number as K2. So I put the equation into this form: d squared psi 2 of x divided by dx squared minus K2 squared psi 2 of x equals 0. Again, I can find the roots of this equation by writing this over here. So I remove this and I write this equation in the form d squared minus, here is minus, K2 squared multiplied with psi 2 of x equals 0. I again have the same form of the equation, but this time we have a negative sign over here. So this term goes to 0. This must not be equal to 0. So I write this as d squared minus K2 squared equals 0. This allows me to write this as plus K2 squared. So I'm not writing the plus over here. And this gives me d equals plus minus k. So this time we have two real roots. K is a real number, so we have two real roots, not complex root. And every root again gave rise to a solution. Therefore, I can write the solution in region 2 over here. Psi 2 of x is again a two-term solution, the superposition, and I write there c exponent minus k1 k2 x plus d exponent k2. This is 2, right? I missed the 2 in the subscript, k2x, and I call this equation 2. Now this is x. Now, I want to further discuss the physics of equation 2. Since we are dealing in the region, second region, therefore this one is one kind of solution, this is another kind of solution, but this solution k is positive. And as x increases, this term goes on and keep on increasing. And when x tends to infinity, this term diverges. And that divergence makes the second solution unphysical, because for physical meanings, the solution must be limited and must not be diverging. So what we want to make this physical, we set d equal to 0. The probability of this, the probability amplitude of this part goes to 0 in order to keep the solution physical. And that allows me to write by setting d equal to 0, that is, I set this term equal to 0 for physical validity. Therefore, the solution in the second region reduces to a single term exponent minus k2x. And this I call equation 3. Now we have the equations for finding wave function in region 1, which is given by this, in the equation for wave function in region 3. But there still needs to do some things because we don't know exactly the values of A, B, and C. And we want to use the conditions, the two very important conditions on a wave function, and those are the continuity conditions. So we know from our previous knowledge that the wave function must be continuous. at the boundary, and the derivative of the wave function must also be continuous at the boundaries. And if you don't know about these conditions, I have a video on them, and you can watch the video on the link in the description below. So if you are interested in, you can go there. And now I want to use the first condition, that is the wave function at the boundary. What is the boundary? This is the boundary. X is equal to 0 must be continuous. Under that condition, continuous means the wave function in this region at the boundary must be equal to the wave function in this region. That is, psi 1 of x at x is equal to 0 must be equal to the wave function in the second region, psi 2x and x is equal to 0. At the boundary, these two equations must be equal, and when they are equal only, then the wave function is continuous. So now if I put the values, and I can write this value for psi 1x, which is a exponent iota k1x is equal to 0 plus b exponent minus iota k1x at x is equal to 0 must be equal to c exponent k2 minus k2x at x is equal to 0. And if I put the value for the wave function at the boundaries, x is equal to 0, the exponent here reduces to 1, this exponent reduces to 1, this reduces to 1. So I'm just getting this very fancy equation, and I call this equation 3, that lengths the probability amplitudes for the incident wave, for the reflected wave, and for the transmitted wave. And similarly, if I use the second condition for continuity, that is the derivative of the wave function must be continuous. No, so then I get this thing, that derivative of psi 1x with respect to x at the boundary x is equal to 0 must be equal to the derivative of psi 2 of x with respect to x at the boundary x equal to 0. So that means first I need to find this side by differentiating the wave function in equation 1, and then this side by differentiating the wave function in equation 3. And I just want to put this equation somewhere over here for later use a plus b equals c, and I call this equation 3. I'm writing this, I am boxing this equation for reference. So I remove this, and I apply this derivative to this form function. So I can write d psi 1x over dx is in fact equal to d by dx of a exponent iota k1x plus d by dx b times exponent minus iota k1x. Right? Now this is very straightforward. The derivative of a constant times a function is equal to the constant times the derivative of function. So I can write this as a times the derivative of exponent iota k1x, and then the derivative of the argument gives me iota k1. And from the second term, I get b times exponent minus iota k1x into minus iota k1. Or in other words, I can write this solution as iota times k1 times a exponent iota k1x minus iota k1 times b exponent minus iota k1x. And if I want to find this at the boundaries, I can write as d psi 1 of x over dx at x is equal to 0 is in fact equal to, I will put x equal to 0 in these two terms. So the exponent in this case goes to 0, goes to 1, the exponent in this case goes to 1, and I'm left with only iota k1 times A minus iota K1 times B. Okay, let me call this equation. This is equation 4 because the 3 we have over here, so this is equation 4, and I call this equation 5. Now I want to find the derivative of this wave function, and then want to find that at x, the boundary x equal to 0. So I write d psi 2 of x equals, the derivative of this is in fact equal to minus k2 times c raised to the power minus k2 of x. And if I want to put the value at x equal to 0, then this thing would go to 0, or the exponent would be 1, and I will just get minus k2c. I call this equation 6. Now, if I put the values from equation 5 in equation 6 in this condition, I then get iota. Let me write that over here. I don't need, I think, this equation anymore. Even if I have the need for it, I would rewrite them. So I just want to put the values in this one equation. I get iota k1 times a minus iota k1 times b equals minus k2 times c, right? And I call this equation 7. Now we have two equations, equation 4 and equation 7, and there are three unknowns a, b, c. So we want to find b and c in terms of a, because a represents the incident amplitude, and that means we would know about the incident wave function. So we want to find b and c in terms of a. That is, we presume that we know about the amplitude a of the incident wave. So with that, I can replace the value of c at this position and can write iota k1a minus iota k1b equals minus k2 times a plus b. Now I can solve this equation for b. So I take b to this side of the equation and a to this side of the equation. And doing that, I can write minus iota k1, and then minus k2 to this side will make it plus k2. b equals minus k2 times a, and this would there would become minus iota k1 a, or I can write b equals minus k2 minus iota k1 divided by minus iota k1 plus k2, the whole multiplied with a. Or I can take iota common from the numerator and denominator, and similarly the minus common to write this into this form, minus iota into k1, and this minus times plus iota k2 divided by minus iota k1, and to make this plus, I would like to write this as minus iota k2 multiplied, the whole multiplied with a. So I can cancel this with this, and finally I can write p in the form minus iota minus would make this minus iota minus, that minus multiplied with this would make it plus, and I need 9. So this one would be minus, and then this minus with this multiplied plus, and the iota, so this one would be plus. That would be in that form. So I write this as k1 minus iota k2 divided by K1 plus iota K2 times A. And now using this value of, let me call this equation 8, now using this value of B in equation 4 to find C, I can do that over here. So I can write A plus K1 minus iota K2 K1 plus iota K2 multiplied with A equals C. Or I can combine these two terms to form a single term by taking LCM. So I multiplied this with A and I write this as K1 plus iota K2 plus K1 minus iota K2, the whole divided with K1 plus iota K2 multiplied with A, and this equal to C. So this cancels with this, and K1 plus K1 is 2K1, therefore I write C equals 2K1 divided by K1 plus iota K2. This defines the times A, and I call this equation 9. So equation 9 defines the probability amplitude C, and this is in fact the wave function. C defines the wave function in this region. We at the moment don't know what kind of wave that is, but that is obviously a decaying function, because we knew that side 2 was of the form, this side 2 of x is equal to C times exponent minus K2x. Since this is a positive number, increasing x would cause this term to decay, so we would have a wave function like this. But there are two things to decide that. And in this region, we have an oscillating wave function. This is an oscillating wave function. So overall, we have this situation. And then there is something like this. We want to find this thing furthermore. So the mathematical portion of the problem has been completed, because we know the probability amplitude C in terms of the energies. K1 is the characteristic of particles that contain energy and mass. K2 is the characteristic of particle in of the potential, because K2 contains V naught in mass of the particle, in energy of the incident particle. So now we have defined the probability amplitudes B and C in terms of the probability amplitude A at this position, A at this position, and the geometry of the problem. The geometry of the problem mean the characteristic of the problem, that is K1 and K2, where K1 and K2 are the characteristic of the geometry and of the incident particle, the energy, the mass. So we can now study the behavior of this problem. But with that said, I would discuss the physics of this problem. I would discuss the results of this problem in the coming video. And for now, I stop here with this with these values. I'll start with the value of C, B in terms of A in the next video. Okay. Thanks for watching.